So this is the second part of the tutorial. In this part, we'll look at methods for CQA retrieval. So basically, methods for retrieval of information from question answer archives. And this is an overview of the kinds of methods that we will cover. We will look at some methods that use translation models, and we'll look at other methods that use topic models, and we'll also consider a method that uses both of them. Then we will turn our attention to neural networks and look at some methods that build upon neural network building blocks. Then a set of techniques that, or rather one technique that works on tensor decomposition, that works using tensor decomposition, and a last method that uses neighborhood-based transformation in order to do CQA retrieval. So the choice of these methods is basically motivated by the urge to illustrate the diversity of technical building blocks that have been used in CQA retrieval. Okay, so let's move on. Moving on to retrieval models for QA archives. So this was one of the earliest papers in QA retrieval. This dates back to 2008, and this was from Xu, Jian, and Croft in CQA 2008. So they use language modeling for information retrieval style scoring. And they explicitly model the lexical chasm using statistical machine translation models. Okay, and let's look at statistical machine translation models. And so whenever we introduce new technical building blocks, I'll start from the scratch so that you understand what is going on. And this tutorial does not assume any kind of background knowledge of the basics of each of these technical building blocks. Okay, so moving on. So translation models are statistical models that are built upon parallel data. And parallel data could be in the form of English and French documents, for example, this pair of documents contain the same information, but one is written in English and the other one is written in French. And there is an expectation that there is sentence-to-sentence correspondence. Okay, so that is a traditional expectation that has been used in building statistical machine translation models. And essentially, these models learn over large corpora of these parallel documents. So you might have a second document, a second pair, a third pair, and many such pairs. And using this, using these pairs of using this parallel corpus, what they built, if you look at it in a very simplistic manner, of course I'm kind of oversimplifying this a little bit, but what they built is essentially something that looks like a matrix. So you have English words as the columns and French words as the rows. And each of the entries in the matrix represents the probability that French word J, so the corresponding row has a word associated with the French vocabulary. The French word FJ, what is the probability that the French word FJ corresponds in terms of meaning to the English word EI? So that's what they try to quantify. So the process of learning this metrics, we're not looking into it because we'll treat translation models as some kind of a black box for the purpose of QA retrieval. So moving on. So this CQA 2000 paper treats question answer corpus as parallel text. So they treat question as maybe English and answer as French. So those are the statistical machine translation models are learned over different natural languages. So this is kind of an application of that, in which they treat question and answer pairs as parallel corpora. And then they learn translation models over them. So you simply use the translation model learning apparatus over the parallel text, over the pseudo parallel text or the quasi parallel text that we get by considering question and answer parts as parallel data. Okay, and if we do that, and this is the result that I got from doing that on a question answer corpus from an IT service desk. And this might be what you get. And let me just highlight a few of these elements to illustrate the point. Okay, so here you can see that disk and full are highly correlated with files and deleted. So there are high probabilities in that encircled region. And similarly, you can see high probabilities in other regions as well. So here you have reported and resolved having a high probability. So the reported appearing in question and resolved appearing in answer. Okay, so that combination has a high probability, and failed comma resolved has a high probability. And you might see that the first part of this matrix that is highlighted denotes kind of domain-specific associations, which are very specific to the QA scenario that we ran this corpus over, which is the IT service help desk. And you might also see that there are a bunch of generic associations that are also achieved by way of this. So failed appearing in the question, leading to resolved appearing in the answer is probably a generic association. So it has nothing to do with the domain of IT support Q&A in this case, which was a corpus that was used in this case. So there are some generic associations, there are some domain specific associations. Okay, so moving on, let's look at how they use this model, right? And so the task essentially is the probability, is judging or scoring the probability that QI comma AI, which is a historical question answer pair, is of relevance in order to address the new question which is represented by Q. So Q is a new question, QI comma AI is a pair from the historical question answer corpus. Okay, so what they do is this one. So don't be intimidated by this equation. It's fairly simple. We look at it part by part. So there is the support of each. So you have an outer product form, which is basically summing up which is basically a product over the words. Each term corresponds to a word in the new question. And the probability of W given QI is the support of the word W from the historical question QI, which is estimated in the in a model similar to language models for information retrieval. Okay, so this is probability of W given QI, the support of each word in the new question from the historical question. And you also have the support of each word in the new question from the historical answer. So the probability of W being generated from a language model that is learned over AI, which is the answer part. Okay. So now there is this interesting middle part, which is where the translation models come into play. So you look at every word W in the new question, and you look at every term T or a word T in the historical question QI, and you multiply these. So the inner the inner summation has two terms within it. So one is the relatedness between W and T, and the second term, which is basically joined with the other one in the product form, is the probability of T given QI, which is the probability of generating T from a language model learned over QI. So here what we are saying is, it is not actually necessary to find W in QI, but it is okay if you can find something which is a word T which is in QI, which is highly related to W as estimated by the translation model. And this entry comes from the metrics that is learned from the translation model. So hope this is clear, right? So we are kind of relaxing the assumption that the same word should appear in the historical historical question or the answer, but we're instead saying that a related word as estimated, or the relatedness as estimated by the translation model, if it appears, then well and good. We'll credit that information. We'll credit that to the score. Okay, so here I'm using a slightly simplistic version of the scoring model that they use, but this captures the spirit of the scoring model. Okay. So moving on, let us look at a new paper, much newer paper from CIKM 2014, which uses topic models. So this is the second. This is from the second category of papers which use topic models. Okay, so this extends topic modeling to community question answering and retrieval. So questions and answers follow the same latent topic. So that is the assumption that they use within this paper. So well, although the questions and the answers that are associated with each other, although they follow the same latent topics, questions are written in question language and answers are written in the answer language. So even though they come from the same topic, they are written in different styles, and the style is referred to as question language and answer language in the paper. Okay, and they use the QA archive to determine the latent topics. Okay, so we'll look at topic modeling in a little bit of detail in the next slide. So that's what we're going to do. So given a set of documents, so here topic modeling, the generic version of topic modeling was kind of designed for capturing the latent set of topics that is represented in a set of documents, in just a set of documents. So this is not QA pairs. Okay, so you given a set of documents, find the latent topics within them. So that's what we are trying to do by means of the topic modeling. So each topic So what is a topic, right? So that so topic modeling defines a topic as a probability distribution over the set of words in the vocabulary. So if your topic is related to maybe Trump, then you might have high probabilities associated with words that are associated with the US politics, maybe things like Senate, Congress, Republican, Democrat, etc., and very low probabilities associated with other words. And I should say here that although we said that the topic is related to Trump, there is no formal notion that there is no formal label for the topic. The topic, a topic is a probability distribution over the set of words, and you might distill it. You might look at it and say that maybe, okay, this one seems like having high probabilities for these kinds of words, so maybe it is related to that topic. There is no topic label that is learned, but just a probability distribution, and multiple of them representing each topic, each probability distribution representing each topic. So let's look at topic modeling, right? So the topic modeling uses a generative process. So this means that they assume that documents are generated using a particular script, and they outline the script. And the script is certain statistical models, which are, for example, a library of topics and so on, which are used in the script. But those are not known. So what they try to do is they use the script, and the script uses some statistics, and this statistics is not known. So, but what we have is the set of documents that are generated using the script, and using that assumption, we try to learn the set of topics that are associated with that set of documents. So let's look at the script by which a document is generated according to topic modeling, according to one basic version of topic modeling. For each document, and we have n of those documents, which is represented by the n shown at the bottom right corner of this tile. So each tile represents a document, and there are n of these tiles, and this is a shorthand to represent that. So you sample a distribution over topics using a global parameter. Let's say that there are 100 topics, and you might sample a distribution which says that which is highly skewed in favor of maybe 3 topics. So let's say topic T13, T50, and T87 have high values, and all the other topics have low values. So that is an example of a distribution over topics, which can be derived using a global parameter, and we don't get into details of the parameter at the moment. And for every word in the document, you sample a topic from the distribution. So you sampled a topic distribution which is highly skewed in favor of maybe 13, 50, and 87, and you might sample it. And for generating each word, you sample a topic from that distribution. So the first word might be sampled from the first sample from that distribution might be T87, and you sample that topic, and that topic is associated with the probability distribution over words, right? And then you sample a word from that topic. Okay, and as you see, the tile notation kind of carries forward within that. So there are n number of words, and there are ni number of words in the ith document, and this thing is repeated ni number of times, right? So that's what is indicated here. Okay, so and now what we have done is we have used a script to generate a document, but we don't have documents are not actually generated using the script. So what we see is the set of words and the set of documents containing those words, right? For every you have seen the documents, and so the gray node is what you have observed, and you're trying to estimate what the values of the Z and T nodes are. So Z is the topic that is used to generate that particular word, and T is the topic distribution that is used for that particular document. Okay, so you're trying to estimate the topic as well as their distributions, as well as the topic distribution for every document. So that's what you do in the case of topic modeling. So you're kind of using the script and assuming that whatever you have seen is generated using the script, and you're working your way backwards and learning the models that could have gone into the script. Okay, so let's look at how these people from CQA in 2014 use this topic modeling thing, right? So so they use an extended version of this topic modeling example of this topic modeling script. So where they have a generative model, or they have a script for generating every question answer pair. So for every question answer pair, QI, AI, and there are n of those, right? And you sample a distribution of the topics using a global parameter. Once again, it's similar to the earlier one. And now you want to generate QI words, or cardinality of QI words, which form the question part of that question part of that pair. For that you sample a topic which is ZQ from the topic distribution and generate a question word, and do that again and again in order to generate as many question words as there are in the question part. And similarly, you do the same thing for the answer part. You sample a topic from the topic distribution, and you get the question and you get the answer words from the sample topic. And here one thing it's useful to note is that even if you sample the topic T13 for the first question word and maybe the fifth answer word, the distribution that is used to generate the first question word is the question version of that topic. Okay, that is a different probability distribution as against the answer version of the topic, which has a different probability distribution. So you will learn kind of twin probability distributions for every topic, and that's what they do. Okay, so some details of the generative model are omitted for brevity, because especially certain things like the quality signal that they use, I've kind of omitted it because I wanted to capture just the spirit of the method here, and you can go back to the paper for the details. Okay, so moving on. So let's see what they do, right? The generative model enables us to estimate the latent topics and their question and answer distributions, and these are then used for scoring. And let's see how they do scoring. So you have the same scoring function, which is the probability that you need to estimate that the QI, AI pair, which is historical question answer pair, is relevant to the new question that you get. We are kind of loosely using the notion of probability. It may not be actually a probability score, because the set of questions are not kind of known, because these are all new questions. But you can think of it just like a score. Okay, so here we do the same kind of summation, which or the same kind of product, which is over every word in the question part. And here you have the same three parts. One is the support of the word W from the QI part, which is basically the question part of the historical question answer pair, and the support from the answer part of the historical question answer pair. And the one significant difference here is, instead of summing up in the middle term over the set of words in the QI, you sum up over all the set of topics. Okay, and then you're looking at whether that topic is well represented within QI. And if that topic is well represented, and if that topic is highly related to this word W that you are looking to score on, then you give a high score. Okay, so here it is the topical correlation of each word in the new question, which is W, with the topical affinity to that same topic of the historical question. So that's what they use. So in essence, they're kind of replacing this PT from the translation model, instead by a topic model, by something from the topic model. So it's not the same metrics. It's not a vocabulary by vocabulary metrics. It's a vocabulary by topics kind of metric. So it's slightly different, but the kind of modeling that they use is kind of very similar to the earlier one. Okay, so moving on, let's look at another work which is also from 2014. So it's called Learning to Suggest Questions in Social Media. We have seen translation models and topic models, so why not use them together? And this work exactly does that thing. So you have a scoring for given QI, AI. So once again, it's not probability; it's just a scoring. And here what you do is you once again have a product over the set of words in the new question. And you take the evidence from the translation model, okay, which is basically the middle term from the translation model term. So here I've used a shorthand. So PT of W given QI, AI, and the evidence from the topic model, which is written once again as a shorthand PZ of W given QI, AI, and those are kind of interpolated using a weight. So alpha is a value between 0 and 1. So you have alpha times the first evidence from the translation model plus 1 minus alpha times the evidence from the topic model. So that's what they do. So this method just simply uses topic models learned from the question part and not the joint QA model. So that's worth mentioning here. So it's not exactly the same kind of topic model that we had introduced earlier. It's a slightly different version of the topic model, which is learned over only the question parts. Okay, so let's see how far we have gotten. We have covered translation models, we have covered topic models, we have covered one method which uses topic and translation models together. So now we will look at neural networks. And before getting into the neural network based method for doing CQA retrieval, we'll need to introduce some basic neural network architectures, right? So that is which might be useful going forward. And then we'll look at tensor decomposition and neighborhood based transformation. So we'll first look at word embeddings, which is one of the basic neural network building blocks that is used in one of these retrieval methods. Okay, so we'll just start with an introduction to word embeddings. So let us say that you want to learn a vector representation for every word, and you have a set of documents, and you want to infer a vector representation for every word that occurs in that document corpus, in a way that the similarity between word vectors kind of captures the semantics of the word or the meanings of the word. So if you have like maybe a word which is highly maybe a word like cat and a word like dog, and those are all used in the pet context, and so they should be highly similar. So the assumption here is that the semantics of a word is determined by the company it keeps. And let's look at how we can learn these vectors, right? So this is a brief introduction to word embeddings. So let's look at a particular toy example to start with, and let's say that a document contains these words: a quick brown fox jumps over the whatever it is, right? And we are looking to generate a vector for each of these words that occur in this document, right? And these words might occur multiple times across multiple documents in the corpus, but we are looking at a toy example to start with. And we need to first decide on an n word window. So here we use a window size of 3. So the vector for a word is determined by is kind of influenced or learned or allowed to influence by the 2 words before it as well as the 2 words after it, wherever it appears in the corpus. So here the is the word that we are interested in, and the two words before it are empty, so we don't need to consider them, and the 2 words after that is quick and brown. So what we do is we just enumerate these pairs. So the has quick in its neighborhood, the has brown in its neighborhood, and then we shift our attention to quick, right? And now you have the same 3 size window on either side. So you would consider the neighborhood the, brown, and fox as well, right? So you would have you would generate these pairs, these 3 pairs, saying that quick has the in the neighborhood, and quick has brown in the neighborhood, quick has fox in the neighborhood, right? So that's what it is. So we kind of generate a whole lot of these pairs, and we'll use them to learn the word embeddings. So let's move on. So we create a neural network which has an input layer and an output layer as well as a hidden layer. So and we'll consider the particular training example the, quick, right? So quick appears in the neighborhood of the word the. So the input layer has as many nodes as there are words in the vocabulary. So there is a node corresponding to the word the, there is a node corresponding to the word quick, and there are nodes corresponding to all words in the vocabulary. And there is an output layer where also you have the same kind of setting, right? And there is a middle hidden layer which you can control the number of nodes, because you're just going to set the number of nodes, and there are 300 nodes, let's say. Typical value is 300. And you have connections going from the input layer into the middle layer, as well as from the middle layer into the output layer. Okay, so there are connections going from every input layer node into every middle layer node, but I'm just representing the connection from the onto all the nodes, and the connection from the first middle layer node onto all the nodes. Okay, so that's what it is. Okay, so now let's look at how we do the training for this particular training example, the, quick. You pass a one hot vector, so that's called a one hot vector, because you have just one. You have just a value 1 in one of the entries, and everything else is 0. Everything else is turned off. So the input layer vector is you turn on the node corresponding to the input and the node corresponding to the word the, and everything else is turned off. And you pass this, so there are some weights that are the neural network, which we'll kind of refine, but you can set them, you can initialize them to something reasonable. There are various initialization strategies. We don't go into those details. And what you expect is, you expect after the end of this process, you expect to get this one hot vector, which is the word quick has 1 against it, has 1 in its output, and everything else is 0 in its output. Okay, so that doesn't always happen as you would imagine, because I mean it's not just trained for this particular example, but you kind of having done this, you kind of evaluate the error that you get in the output layer against this vector that you expect, against this one hot vector for quick that you expect, and then you propagate the errors backward. Okay, and then you do this using every example from the previous slide. You did this for this example, and then now in the next iteration you do it for the next word pair, and so on and so forth. And at the end of it all, and you do multiple epochs maybe, and at the end of it all you get a trained set of weights. And what do we do with that, right? Then we throw away the output layer weights. We throw away the weights going from the hidden layer to the output layer. Okay, and now what are we left with? We are left with these weights for every word in the input layer. We have a set of 300 weights going into each one of the input, each one of the hidden layer nodes. So use the 300 weights on the edges from the as the vector for the. So you have a 300 length vector, right? And that is a vector corresponding to the. And you use the 300 weights on the edges from quick as the vector for quick, and so on and so forth. So what we just saw is a basic version of the word-to-vec model. It's a basic, it's one of the basic versions. There are multiple versions, but it's just a basic version. And this kind of suffices for our purposes because we are looking at CQA retrieval methods, and word embeddings is not exactly the actual focus of our talk. Okay. So let's look at how we can. So we saw how we can generate a vector representation for every word. Now, how can we generate a vector representation for every document, right? So we have a set of documents, and we got these word pairs from every document. From every document, you generate a bunch of word pairs, and you put them all together and learn this architecture, right? So here, what we do is, so we can represent this architecture in kind of a compressed form by saying that all the words in the input layer, the words in the output layer, there's a hidden layer as well, and you have the document IDs as yet another input, yet another set of nodes in the input layer. Okay, and this is one modification over the basic word-to-vec model. So you have document IDs, and now the training example is no longer a pair, but it's a triple. So if you got the word pair the comma quick from document doc1, then you set the document. So this doc IDs has an input node for every document ID. So for doc1 there is an input node, and you turn 1 and you give 1 as the input on that. Everything else would be 0. All of the doc IDs would be 0, and you would set a one hot vector for the words for the word nodes as well. And then you do the same training, right? So the training example from another thing could be doc5 comma word comma embedding. So instead of training over word pairs, we're training over document input word output word triples. So after the training is complete, what you can see is you get for every document ID, you also get 300 weights going from that document ID onto the nodes in the hidden layer, and that is a vector representation for the document, right? And so it's basically by doing this training process, by extending the basic word-to-vec model, by adding a bunch of extra nodes to the input layer, what we get is we get a document representation as well, which is called a document embedding. So we look at another building block in the neural network space, which are called autoencoders. These are fairly important, and these are heavily used in unsupervised learning scenarios over and much beyond CQA retrieval, as is the case with word embeddings as well. So here what you try to do is you pass on, you have multiple hidden layers. You have an input layer and an output layer, and there are multiple layers in between, which are called the hidden layers. These hidden layers progressively are smaller and smaller until a point, and then they start becoming larger and larger. Okay, so what does this mean? So the training example that how do we use this kind of a network? The training example is basically you give a vector in the input and you can expect a vector in the output, and this can be used for one hot vectors or for any kind of vectors. So you have a vector representation, you give it in the input, and you expect to get that same thing in the output, and if there is a difference, then you pass the errors backward, right? And there are of course other nitty-gritty details which I'm not getting into details of. So the training examples are the training example in the earlier case, there was a target word and there was an input word and an output word which were different. Here the training examples are all the same. It may not be one hot vectors, but it's the same. The input is what you expect in the output as well. And it's hard to expect that you would get the same thing, because there is a lot of compression happening as you go along. You're getting into a smaller hidden layer representation, and from that hidden layer representation, you're using the weights to project them back. So because these hidden layers in the middle are much smaller, the autoencoder cannot simply memorize what is given in the input, and then it cannot do kind of rote learning in some sense. Okay, and the middle layer is generally called the code. So, and then you throw away the output part, everything after the code part, much like we did in the case of word embeddings, in the case of the word embedding network, and use the representation as the code layer, as a compressed representation of the output. So after all this training over a bunch of vectors, you use this kind of code representation for each vector as a compressed representation of the input. Okay. So let's look at word-to-vec, word embeddings and autoencoders, and the versions that we saw so far. So both train on a prediction task. Okay, so you have an input word, output word pair. So that is what the word embedding trains upon, and the autoencoders train upon the input comma input, which is basically saying that you want to regenerate the input and the output. So the autoencoders train on reconstruction, word-to-vec trains on context prediction. The intent is to learn a meaningful representation for usage in other tasks. So it's not actually a prediction problem that we're attacking. We are throwing away the prediction part of it and learning the intermediate representation. So word-to-vec learns a word representation, autoencoders learn a compressed representation. So this is one way to draw a parallel between these two building blocks. So let's look at how they are used in the case of CQA retrieval, right? And this is from the Knowledge-Based Systems journal in 2016. So this is much later work. So what they do is they use separate autoencoders for questions and answers, and they fine-tune the autoencoder so that the representation for the questions and their best answer are close to each other. So let's look at each of these steps in isolation. So you want to learn separate autoencoders. So what you do is you take the question answer pairs, right, and throw away the linkages. So you get a set of questions and a set of answers, and you have thrown away the linkages. You've forgotten which question represents which is associated with which answer. And you pass all the question representations. You can take the document embeddings or some other metrics, some other vector representation. You take the set of questions, learn an autoencoder. You take the representations, learn an autoencoder. You take the set of answers, you learn an autoencoder over them. So that is separate autoencoders by forgetting the linkages between the question answer pairs. So you're taking question corpus, answer corpus, and learning two separate autoencoders. So now you throw away the output part of it like we did earlier. And now we'll do the fine tuning for QA correlation. And how do they do that? For that, they take a question, they take a best answer, and they take another answer, which could be an answer for another question. Okay, so you have these triples. So and you pass this and you pass each one of them through their respective autoencoders. So for the question part, you pass them through the question autoencoder. So which is weights learned as WQ, and for the best answer as well as the other answer, you pass them both through the same answer autoencoder, right? And so the weights are the same, WA and WA. And you get intermediate representations. You get a compressed representation of other answer A prime. You get a compressed representation of the question Q. You get a compressed representation of the best answer A. And what do? You compute the similarity between the Q and between Q and A, and you compute the similarity between Q and A prime. And if we have learned something meaningful, then what it means is we would have the similarity between question and answer, Q and A, as being more similar than the similarity between question and A prime, because A prime is an answer from another question, right? So if that is not satisfied, then the autoencoders have not learned learn to associate the answers associate the questions with their best answers, which kind of is not expected at the beginning of this step because you have learned separate autoencoders. But by using this kind of by using what we'll just see now, eventually we expect the autoencoders to be able to correlate answers with their best questions with their best answers. So if the similarity between the question and the other answer is higher than the similarity between the question and its own answer, then you propagate the errors back. And eventually, if you do this over a set of triples, at the end of this learning process, what you get is probably the weights of autoencoders. The weights that you started off with from the autoencoders are kind of tuned slightly in a way that they can associate the question with its best answer as against the question with other answers, right? So that's what it is. So now we will look at we will look at another paper. So this is from IIII 2015. So maybe just to complete the earlier thing. So once you do that, you can potentially use that model for retrieval, right? I will leave you to look up the details in the paper, but I think it's kind of straightforward from here on, as you might be able to see already. Okay, so moving on to the next paper, which is question answer matching for CQA systems. So this is from IIII 2015. Okay. And this uses a very different approach. So they learn a neural network pipeline that can quantify the match probability of any QA pair. So what they do is they train the neural network using historical QA pairs that have a good match. And now you have a new question. You kind of try and see which are the answers to which it can match well, right? So let's look at the details of it. So you first learn a QA matrix. So if you take a question and an answer, and the question has 5 words and the answer has 5 words, then you get a 5x5 matrix, right? And depending on the weight associated, depending on the frequency of correlation. So if the second question word is associated with the third answer word or whatever it is, right? I mean, if the word embeddings are close to each other or something, essentially you give a high value there. You have a higher density there. I think you should go into the paper to look up the details, but I'm just giving you a high level overview here. And so if you take every question answer and QI comma AI or Q1 comma A1 might give you a 5x5 matrix, Q5 comma A5 might give you a 10x10 matrix or 5x8 matrix. So to kind of put them all on the same footing, what they do is they take the words in the longest answer, the words in the longest question, and if your matrix is much smaller than that, then you kind of tile it. You put that at the top left corner, and you kind of tile it in such a way that you fill up all the elements here, right? Okay. So what you get is you get a matrix of corresponding to n by m, where n is the words in the longest answer and m is the words in the longest question, right? And that is a matrix representation of your question answer pair. And what you give is you give this matrix representation onto a big neural network pipeline. And as you would imagine, the first layer of it is a convolution layer, then you have a max pooling layer, and so on and so forth. And eventually at the end of it, what you get is a quantification, which is basically the match probability. The probability that this question answer pair is a good match. Basically whether the question is the linkage between the question and the answer is a good quality linkage. So the sequence of layers that finally yield a quantification of the match probability, and you have a lot of historical question answer pairs that are very good, because you know that the questions were posed against those answers. The answers were posed against those questions and so on. So you use that to train this whole neural network, and to eventually get a neural network that can take a question answer pair and give the match probability between them. For a new question, one could find historical questions that have the highest match probability, right? Or historical answers that have the highest match probability. Assume it's answers, because we are learning question answer matching here. Okay, so that's what they do. And now we have completed a bunch of methods that are 2 methods that look at neural networks. We also looked at some of the basic building blocks in neural networks. The things that are left are tensor decomposition and neighborhood-based transformation. Before starting to look at tensor decomposition-based methods, we'll start with some introduction to some metrics methods. Okay, so we'll start with an introduction to SVD and latent semantic indexing. And there's a quick intro to those methods. So let's say that you have a term document matrix, and this is kind of old-fashioned in some sense. Nowadays, you represent documents by way of vector representing the word document embeddings. But let's say there is a term document matrix, right? And now you have each entry in the matrix is the frequency, is some kind of normalized frequency of the term in that document. And now you can decompose this matrix into 3 matrices, into a product of 3 matrices. So one is the number of terms times r, and then one is an r by r square matrix, and then there is an R by the number of documents matrix. Okay, so you might see that the dimensions are all right, terms by R, and if you multiply it by an R by R matrix, you will get a terms by R matrix, and if you multiply terms by R matrix with an R by docs matrix, you get a terms by docs matrix. Okay, and then we enforce this condition that that this R by R or the diagonal or the square matrix is going to be a diagonal matrix. So anything outside the diagonal is going to be 0, right? All entries outside the diagonal are going to be 0, and R can be as high as the number of singular values, but if you choose a smaller R, which is basically, I mean, you can choose R. If you choose a smaller R, you would choose the top singular values, the top R singular values, and that would yield an approximation. So you may not get an actual reconstruction of this matrix on the left hand side, but you might get an approximate reconstruction of it, in the sense that the entries are more or less similar. Okay. So let us look at how we can use SVD and LSI. Okay, and let us say now that you have this decomposition and you have come up with these three matrices, the product of which approximate the matrix on the left. And now if you look closely at the R by docs matrix, what you have is you have as many columns as the number of documents, and the ith entry or the ith column of that matrix corresponds to the ith document, and that yields an R length vector, right? I mean, so you're getting an R length vector for that document, and this low dimensional document representation is thought is kind of shown to be more meaningful than just TF-IDF vectors, which would basically be what you would get if you take a row out of the matrix on the left hand side. Okay, the better quality of representation on the right hand side is kind of intuitive and also not so intuitive both at the same time. It's kind of intuitive in the sense that you're making use of the whole corpus in learning this decomposition. So this new latent vectors or the small vectors, the R length vectors that you learn, have an opportunity to use some information from across the corpus. That is one thing. But on the other hand, R is typically much smaller than the number of terms, so it might lose some expressive power because of the length. If you choose a low R, then you might get a bad semantic representation, not so good semantic representation. Okay, so let's move on. The low dimensional representation is more meaningful since the decomposition uses cross-document information, so it uses corpus level information. So moving on, let's look at tensors and tensor product now that we have seen matrices and matrix decomposition. So tensors are simply higher order matrices. Okay, and if you have an A by 1 length matrix, A by 1 matrix, which is basically a column vector, that you would generally just call it a column vector or a vector. And if you take an A by B matrix, and that is generally referred to as a matrix, and if you have 3 dimensions in the matrix, so essentially it's a higher order matrix, A by B by C. So if you want to pinpoint to one entry in this higher order matrix, you need to specify a value of A, specify a value of B, specify a value of C. So you need to represent all the 3 dimensions in order to get to an entry, unique entry within this tensor. So this higher order matrices are called tensors. Now let's look at tensor product. Let us say that you have an A by B by C matrix, A by B by C tensor. Okay, now you can multiply on the second phase. Okay, on the second FAC, the second phase of this tensor can be multiplied with a matrix, and let us say that the matrix is B by D. So since you're multiplying it by the second phase, we're just numbering phases based on the order in which we're writing the dimensionality of this tensor. So A by B by C, and if you multiply it by the second phase, then it needs to be a B by D matrix where D is any value. And what you would get by this multiplication would be an A by D by C matrix. Okay, so you've replaced B by D in the course of multiplying this tensor with a B by D matrix on the second phase. I'm using phase in a kind of a loose terminology here, but just to convey the idea, because we have this kind of a pillar and the phases are kind of more easier to relate to. So xn, which is basically multiplication on the nth phase, changes the nth dimension of the tensor. So that's what happens. Okay, so let's move on. And there is this work called Latent Semantic Tensor Indexing for CQA. This is, I think, a short paper in ACL 2013, but it's interesting because it uses a different school of methods, which is tensor decomposition for the purpose of CQA retrieval. Okay, so they represent each QA as a question title, question content, and answer triple. So it's not just a question and the answer. It is a question split into two parts, which is typically the case in the case of Yahoo Answers or Quora. You have a title of the question that appears also as the title of the web page that hosts the question, and then there is a much detailed content part of the question, which is a question content, and then there is the answer. So you model the data set as a tensor, and then you apply tensor singular value decomposition to get a low dimensional representation and do retrieval in the low dimensional space. So much like you do retrieval in the case of metrics SVD, you get an R dimensional vector for every document, and you can do retrieval using that R dimensional vector. Basically, if you get a new document, you can just compare and then use a measure of similarity to rank the documents in the data set. So similarly, you can do a retrieval in that low dimensional space using the lower dimensional representation that you get for a CQA pair. CQA triple in this case. So let's look at more details about it. Okay, so they want to have a tensor, right? And this tensor is built as follows. So there are the number of QAs, okay, on one side of the tensor. There are the number of terms on the other side of the tensor, and as we said, there are three parts to every CQA. One is a question title, the other one is a question detail, the third one is the answer. So each the question title, the question content, and the answer. Okay, so each fiber in this tensor, each horizontal fiber in this tensor, is essentially a TF-IDF vector of one of the parts of one of the QAs. So you choose the QA, you choose the QA, and you choose the part, and then you get a fiber, which has as much length as the number of terms in the vocabulary of the data set. So each horizontal fiber is a TF-IDF vector or any other suitable representation of one of the parts of one of the QAs. Okay. So let's move on. Now you have this tensor, which is number of QAs times number of terms times 3, and you can decompose this tensor into like one tensor and 3 matrices, which we'll show now. You have a tensor of R by R by R. Okay. On the first phase, it is multiplied by a QA's representation. And on the second phase, it's multiplied by a terms representation. On the third phase, it is multiplied by a number of parts representation, right? And this is basically an R by R by R tensor. So by multiplying with the QAs, you replace the R on the first phase with the number of QAs. By multiplying the second phase with the number of terms, you replace it by the number of terms, and by multiplying it by the number of parts, and then you replace it by 3, which is the number of parts, right? So hopefully the dimensionality thing is kind of correct here, as you might see. Hopefully it's conveyed that it is correct here. Okay. So let us try and see how this can be used in order to in order to do retrieval in the CQA space. For a new question, use the terms matrix to get to a smaller space and compute the similarity in the smaller space. Okay. So for a new question which has 1 by terms by 3, okay, and this is essentially you have all the 3 parts if it's a CQA pair or a CQA triple, question title, question detail, and answer. Then you have this whole tile, basically 1 by terms by 3. And then you multiply it by the number of terms, by the terms matrix that you got from the previous decomposition, and what you get is a 1 by R by 3. 1 by R by 3 essentially means it's an R by 3 matrix which has a height of 1, right? It's trivial in matrix. And now you have 3R number of values, which is basically arranged in the form of this tile, which is a lower dimensional representation of this new question, right? Of this essentially the new question, and then you can quantify the similarity between R by 3 matrices of historical QAs and return the most similar ones. So instead of computing in the case of SVD, we saw that we have this R length vector. Now you have a 3 by R length. Well, it's not a vector; it's a 3 by R length, 3 by R matrix, and then you compute the similarity in that lower dimensional representation, and that's what you get. Okay. Essentially, you can use that similarity as kind of a scoring function and retrieve the top scored CQAs in response to this new question. Okay. So that's what it is. So let's move on. Right, and now what we are left with is this neighborhood-based transformation in terms of the school of methods for CQA retrieval. Let's look at the neighborhood-based transformation approaches. But before that, once again, as we did in the earlier case, we will provide some introduction into some classical work in neighborhood-based transformation. So, which is basically this work called Manifold Learning and Local Linear Embedding due to Rowels and Saul from Science 2000. Okay. So let us say that you have an r-dimensional, you have an n-dimensional space, which in this case we can approximate it by a 3-dimensional space. You have this kind of an aluminum foil which is curly, so it has a 3-dimensional extent. Okay, and you have data points in the space, and we're not talking about QAs anymore. We are not talking about QAs for the moment. We're talking about simple data points, and there is a data point in this 3-dimensional space, right? And there is a local neighborhood of that data point. And if you look at the local neighborhood of that data point, you might, because it's an aluminum foil, and if it is actually an aluminum foil which is curled around, then you would see that the local neighborhood of that data point is going to be a much lower dimensional space, which in this case would be a 2-dimensional space, right? And if you take another data point elsewhere in this n-dimensional or 3-dimensional representation, you might see that its local neighborhood is also a 2-dimensional space. So to draw a back comparison, you can the Earth is a 3-dimensional space, right? So, but whereas if you stand on one point in the Earth and then look around you, you would find that it is more or less. I mean, if you're not considering the height dimension, it's more or less a 2-dimensional space. So, but actually, if you patch together all these local neighborhood points, and they need to be patched together in the form of a sphere in order to get to what the Earth would look like. So that's a bad comparison, but hopefully it conveys some point. Okay, so now you have these. For every data point, now there is this local neighborhood which is lower dimensional, and so around each data point, the neighborhood is kind of 2D. It may not exactly be 2D, but more or less 2D. And you do a transformation of this entire data set, which kind of takes these low dimensional patches and places them together in this 2-dimensional space, in this R² space, right? How do you combine all these low dimensional patches to get a lower dimensional representation for the entire data set? So that's what this paper talks about. Okay, we might get into some more details about it, but largely we will be using this kind of a thing as a black box, which is basically you have a higher dimensional representation. You assume that the data resides on a manifold, which is like a curly surface, in which the local neighborhood is all a lower dimensional space, and you're trying to achieve basically a lower dimensional representation. If it were a true aluminum foil in which these data points were residing in, and this aluminum coil was curvy, what you're trying to do is just stretch it and place it in a 2-dimensional space. But I'm of course approximating this a little bit and using some kind of loose terminology, because by simply stretching it, you may not be able to preserve the entire neighborhood properties. But essentially that's what you're trying to do in some sense or the other. So let's look at what they do. Right, in phase 1, they summarize the neighborhood properties of the original space. And let's see what it means. So you have this data space, higher dimensional space, and you take this data point, you look at the 3 nearest neighbors, and this 3 is a parameter. You can change it to anything that you like. There's 3, you look at the 3 nearest data points, and you find a set of weights for each of these 3 neighbors, such that the linear combination using those weights closely approximates a black point. So essentially what you're learning is you're doing a local optimization problem for every data point, and identifying a set of weights W1, W2, W3, such that W1 times the first neighbor plus W2 times the second neighbor plus W3 times the third neighbor yields a close approximation of this black data point that you're interested in. In this case, it so happens that they lie in the convex hull, and so essentially you can get an exact reconstruction of that black data point. But in cases where they all lie in one side, you can get only an approximate reconstruction. Okay, so for each data point, you find the k nearest neighbors and their associated weights that would allow you to reconstruct that data point in question. So that is a neighborhood summary, the k nearest points and their weights. And now what they do is do phase 2, which is basically learn a lower dimensional space that respects the neighborhood properties of the original space. So what you're trying to do is learn a lower dimensional space of all the data points, including this black one and its 3 nearest neighbors, and every other black data point and their 3 nearest neighbors, in a way that the W1 times that first neighbor essentially is not the first neighbor in this new space, but the first neighbor in the original space, plus W2 times the second neighbor plus W3 times the third neighbor. And when you do the linear reconstruction using their representation in this new lower dimensional space, you get close to the black points representation in the new lower dimensional space. So that's what they're trying to do. Well, I'm not going to get into details of the optimization problem here, but hopefully you get the point that you learn the neighborhood properties of every data point, and you kind of learn a representation of all the data points such that the neighborhood properties of each of them is kind of respected as much as possible. You may not get an exact thing, but you're trying to do an optimization which would preserve some data points neighborhood slightly more than the others, but essentially you're trying to optimize for an objective function that takes the sum of all these reconstruction losses. So we learn a single lower dimensional representation across all data points. So the neighborhood of some data points in the original space may be more preserved than others just because of the optimization. Okay, so let us look at this paper, which is with which I was also involved in. This is EMNLP 2017, which proposes to use this neighborhood reconstruction approach in order to do CQA retrieval. Okay, so the idea is to extend local linear embedding, which is basically the paper that we just described, to 2 more data from CQA. So in phase 1, we kind of de-link the question and the answer parts, like we did in certain other cases. For example, you might remember that to learn autoencoders, we de-link the question and answer pairs. So we are no longer considering them as pairs. It's a set of 1,000 questions here, set of 1,000 answers here, or whatever be the number of questions and answers that you have in the data set. And you learn the neighborhood separately, considering Q and A as separate data sets. And then in phase 2, you learn a unified lower dimensional representation for QA pairs, where the separate Q space and A space neighborhoods are both respected as much as possible. So you're trying to learn a single representation, a single vector for every QA pair. So it was a single vector for the question part, another vector for the answer part. Now you're trying to collapse them into a single vector. Now you have this question that you have this neighborhood representation neighborhood summary coming from the question space, the neighborhood summary coming from the answer space. So you trade them off and learn this representation such that the neighborhoods from either of these spaces is preserved as much as possible. You can have a weighted sum, as we'll see soon. So let's look at phase 1 and phase 2 in a little bit more detail. Okay, so phase 1, you take the Q space and you take the A space. So Q and A space have questions and answers, and they're initially connected, but you forget these connections. Okay, you're no longer using these connections in this space. And to learn the Q space neighborhoods, for every data point, you take the K nearest neighbors, find their weights, solve the local optimization problem, and you summarize the A space neighborhoods as well. And then you go into the second phase, which is basically trying to learn a representation in a unified representation in the lower dimensional space. Now you bring back these linkages between the question and the answer parts. Each point in the new space is associated with a QA pair. Okay, so essentially trying to compress these links or compress these edges in this representation, in this illustration, into points in this in the right hand side. Okay, so each of these edges will give you a point, and these edges are connecting the question part and the answer part. So each point in the new space is associated with a new QA pair, and there is a neighborhood coming from the there is a neighborhood for each of these edges. There is a neighborhood coming from the top part of the top end of the edge. There is a neighborhood coming from the bottom end of the edge, which is basically the Q space and A space neighborhoods, and you try and preserve them as much as possible. Okay, so moving on. Well, so basically what we are trying to do is we are trying to take this data set of QA pairs, so Q1 A1 up to Qn An, and we're learning a lower dimensional unified representation, which is U1 U2 up to Un. And the loss function looks like this. I'm not getting to details of the math here because that's not my that's not my intent to do in this tutorial, because we're talking about things at a higher level. So you're trying to minimize this objective function, which contains 2 parts, and they are summed up using a weighted sum. So the first one is the loss of reconstruction of the Q space neighborhood, and the second one is the loss of reconstruction of the A space neighborhood. And it's easy to generalize to more spaces because you can simply take it and add one more term, which is plus gamma times the loss of reconstruction from a third space neighborhood. So if you want to treat question answer pairs as a triple, then you can very well do this. It's very easy to extend this work into that space as well. Okay, so that brings us to the end of this neighborhood based transformation method. So we have looked at methods for CQA retrieval, which do translation, which make use of translation models, which make use of topic models, which make use of both of them, which make use of neural networks, in particular autoencoders and so on, and tensor decomposition. And we finally, at the end of it, we looked at neighborhood based transformation methods. So let's see where we are in this tutorial. We had this huge task landscape. We spent an enormous amount of time now to just look at the retrieval part of it, about an hour, I suppose, to look at the retrieval part of it. And because that is the most popular research field in CQA analytics. If you look at the papers that have been coming out in that area. Now we will look at one or two methods of each of the other kind of tasks in CQA analytics, and that will be continued in video number 3. Thank you very much.